Welcome everyone to another lesson on Khadija Academy. Before we start this lesson, hit the subscribe button, the notification bell, and the like button for the YouTube algorithm. Now let's go and start our lesson. What if we decided to use a closed loop control? In a closed loop, we take feedback, we give pulses in order to achieve a certain control, and we will see how much we are far from our final goal. Okay, so we use a feedback control, which is very important and the one which is widely used, because we would like to see what will happen at the terminal. Is our current or is our power is achieved, or reactive power is achieved or not? Should our control becomes more aggressive or less aggressive? All of this is achieved using the PI controllers, for example, like this. So we know that the active power is controlled by direct access current, as we have seen here, and the Q is controlled by IQ, as we can see, by IQ. That is exactly what we did, that we took the difference between reference power, the power which we need, and the current power produced by the DG itself. We compared compared it with each other by subtracting them. The error is given to a PI controller that minimizes this error. It wanted to make this error equal to 0. When this error reaches 0, it means that the power produced by the DG is exactly equal to the reference power, right? So the PI control gives us a value which is proportional to what is happening to the error here. Similarly for Q, by looking at the difference between actual Q and the reference Q and the actual Q, it gives us an error to a PI controller that gives us the value of quadrature access current, right? Again, the same steps. This part here is exactly the same part here. Okay, nothing changed, with the same angle of transformation to make VBCC oriented on the D axis. Okay, the difference here is that one point here, or an additional part, is that instead of controlling reactive power, you can control voltage at BCC, right? Voltage at point of common coupling. By controlling voltage, you can control the voltage here, right? So someone will say, what does this have to do with IQ? Remember that we have two quantities in electrical generators which are related to each other. We have frequency or active power, and frequency or speed of the generator are related to each other. Okay, they are related to each other. Similarly, for reactive power, Q or reactive power and V terminal, the terminal voltage, are also related to each other. So for example, we can, by controlling Q, we will be able to control the voltage here, right? Voltage at BCC. By changing how much reactive power injected, we can change the terminal voltage, right? That's why we can replace Q by VBCC. By getting this error between the reference value, let's say 1 per unit, and the current VBCs, the current voltage here, by comparing it to each other and giving the error to a PI controller, it can give us the IQ need, the quadrature access current needed to achieve this function. Why? Because IQ control reactive power, which is indeed control VBCC. Or even if we control VBCC, we can control reactive power. Okay. However, there is something which is very important. You can see that it is a selector. We can select Q or VBCC. You cannot control them together. You can say, hey, I would like Q to be 0 and I would like this to be 1 per unit. You can't do this. You can't control these two together. You have to select which one you are controlling. By controlling VBCC, you will achieve a certain Q that will lead to 1 per unit. Or if you control Q, you will achieve a certain voltage that will lead to this Q. Okay, so they are related to each other. They are coupled. You can't decouple them. So active power and frequency are coupled. Reactive power and V terminal are coupled. By using ID and IQ, you can select which one you are going to control, active or frequency, or reactive power or V terminal. Okay. Another point here is that if you select the voltage regulation, which is VBCC, it means that the static synchronous generator works as a PV node. PV node meaning photovoltaic, but a PV, it means that you can control B, which is active power, and V, which is the voltage or terminal voltage of the connection at the grid. Because as you can see here that if you select voltage regulation and active power, you are controlling P and V. That's why it's called BV. If you select the Q, it will be BQ because you are controlling active power and you are controlling Q, BQ. Now the Q value here, the reference Q value, actually it determines what power factor at which we are working at. So if I select Q to be equal to 0, I don't want any reactive power from this generator. I want only active power. Okay, then the apparent power will be only equal to P, right? So this will be small size and low cost of generator, right? Only active power needed. And the Q 0, it means that this one, our static synchronous generator is, or the interface is working at unity power factor. The generator is at unity power factor. Q equal to 0, the generator works at unity power factor of 1. Why? Because only gives power, active power, and the Q equal to 0. What if I selected Q to be Q load? In this case, the grid itself will be at unity power factor. Why? Because the grid will only give active power, right? Because the Q needed for our load, Q of the load, is taken from this synchronous generator. The grid will give only active power, making it working at unity power factor at the point of common coupling, of course. Okay, because we don't take any reactive power, we only take active power from the grid. Okay, however, this will lead to making the power needed from static synchronous generator to be active power plus Q of the load. Making our S will be root B square plus Q square, making it higher, which means we will need higher cost of static synchronous generator to achieve both active and reactive power. Thank you for watching this lesson. I would like to invite you to our academy, Khadija Academy Premium membership, which will help you learn more about electrical engineering. In this academy or in the academy membership, you will find that we'll have more than 100 courses in math, electrical engineering basics, power engineering career preparations. For example, we have electrical design, we have courses on electric circuits, power electronics, ETAB, MATLAB, solar energy, wave energy, wind energy, and much more. You can join our membership for just a small fee per month, or you can just have a lifetime access in which you will get all of current courses and classes, and you can have them forever. And not only this, but any new courses that will be created, you will be able to watch it for completely free. So what are the classes that I will learn in this membership? You will find different classes in electric circuits. You will find in transformers, magnetic circuits, machines, power electronics, load estimation, lighting design, lightning also design, earthing system, cables, generators, light current systems or low current systems, off-grid design, on-grid design. Very lots of classes and courses in different topics.